opportunity to have Abdul Qayyum with us, and he's originally from Sargodha, down in the Punjab, and he attended the university in Punjab University in Lahore, and then he went for his PhD at Utrecht in the Netherlands, and right now he's doing a postdoc, and so he's had a lot of experience both in Pakistan, in the academic environment in Pakistan, and then also in Europe, and I will point out that we've got several speakers lined up after today's presentation. Next week we've got Catherine Badgley from the University of Michigan, and she's going to be talking about her work together with the Yale-Harvard GSP collaboration, looking at paleo environments and evolution of animals in the Potwar Plateau. And then we've got Humad Ghani coming after, and Doug Burbank and Mohammed Akbar Khan from Lahore. They're lined up as our next speakers following today's presentation. And these talks are coming to you once a week. If you're in Pakistan, it's about 9:30 in the morning, and we would invite you to participate each week. And we will have a flyer. There'll be information ahead of each presentation, so you'll be able to know what's going on. But we're going to have Abdul's talk will be about 45 or 50 minutes, and then we'll have a little bit of time for questions and answers afterwards, so there can be some discussion. And you can either use the chat, or you can raise your hand, or you can just open up your mic and ask a question. We would ask you, though, for the most part, to put yourselves on mute so that we are able to hear the talk as quickly as possible. And without further discussion, I'm going to turn the floor over to Abdul Qayyum, and thank you very much for being with us very early in the morning from the Netherlands.
Thank you, Bob, for the generous introduction. Hi, everyone. Good morning. My name is Dr. Abdul Qayyum. I'll be presenting today. This part of a presentation actually belongs to my PhD work that I did a couple of years ago. Nowadays, I work on a bit different scale, on a larger scale, on the scale of geodynamics. But still, I'm working on the same area about the India-Asia collision, and I'll be talking about that in a detail, and I'll try to link this large-scale tectonics to the basin-scale tectonics. So if everything is, if you guys can hear me and everybody's there, I can start.
Yes, please.
Yes, you can.
Okay. So I'll be talking about. So this is the outline of my presentation. I'll start with the introduction, and then I'll move to the India-Asia kinematic reconstructions. We will see back in time that how this India and Asia convergence actually happened and how much amount of lithosphere has been consumed. And then we move to the stuff that is under the India-Asia. I'm talking about the monitored tomography, in which we will mostly focuses on the northwestern margin of India. And then we will move toward the northwestern Himalayan front, where we will see the different thrust and fold belt and how does they evolve. And then we will move on to the Potwar Plateau and the salt range. And especially the stresses, how does this large-scale tectonics influence the stress within the Potwar and the salt range, and how they develop the vertical axis rotations of Potwar and salt range. And then I will move to I will discuss a bit about the regional cross-sections and the amount of shortening within the Potwar and salt range. And then we will compare with this amount of shortening with this Indian convergence and how much convergence actually compensated within Potwar and salt range. And then we will move to the end part of the presentation. So if you look at the tectonic elements of India-Asia collision, here you have India. We're all familiar with that. And especially with the northwestern margin, we have BO, that is Bela ophiolites. So this is the oceanic floor that has been exposed within Pakistan. We have Muslim Bah ophiolite, we have Waziristan host ophiolite, we have Kabul Altimore ophiolites, and then we have the Greater Himalayas and the Tibetan Himalayas. As you can notice that the Tibetan Himalayas is actually gradually pinches out towards the northwestern margin, and we don't have the occurrence of the Tibetan, the continuation of the Tibetan Himalayas in northwest Pakistan. And then we have the occurrence of Kohistan and Ladakh. That is the U-shaped band, as you can see with my pointer. And then we have Shoyok Suture Zone, that is the northern margin of the Kohistan and the Ladakh. And then we have Karakoram and the Pamir Trains. On the west, we have a couple of different Eurasian terrain, which are known as the Helmand Block. And this is nowadays a part of Afghanistan, and which is the other side of the Chaman Fault. And we have a small block known as the Kabul Block here. That is the eastern side of the Chaman Fault, which is also representing a different unit. And then we have the Herat Fault, that is present in the north of the Afghanistan, and which separates this with this Tarim block and the Asian trains. As you can see, that there's occurrence of quite a different ophiolites, like Spontong ophiolites in India, and known as the Indus-Yarling Suture Zone, Indus-Yarling ophiolites. And in the north of this Indus Suture Zone, you have the Lhasa, which is the part which actually drifted away from India and collided with the Eurasian terrain at 130 million years. And then this Tibetan blocks, Changtong and Somponggazi and Northeast Tibet. So this is the general overall architecture of the India-Asia collision. And now this is just the same figure colored differently at a 0 MA. This is the present day configuration of India-Asia. But as I move back in time, what was the situation like 30 million years ago? How does this India look like before collision? So what we do here is we use the paleomagnetic data to confine the constructions. And we use the paleolatitudinal configuration of different ophiolites and different oceanic floor, different oceanic floors, and then we can constrain them back in time by constraining their paleolatitudes. So the configuration for like 30 million years ago is like that. So the northern margin of India is actually collided with the northwestern Asian trains, and you have the collision first occurring along the Kabul block, and the ocean basins are closing. But this is actually the time when actually continent-continent collision happened. But the collision it's not like we know that the plates, both of these plates are continent-continent, but actually collision initiated way before that. So at a 58 MA, we have the first impact of the Indian lithosphere that is collided with the Greater Himalayas and the Tethyan Himalayas. But this piece of Indian lithosphere is not present anymore. You cannot find this because it's been subducted. So once you have the subducted, perhaps the oceanic lithosphere, you got the remnants in the subsurface, but you cannot find. You can just find some slivers at the suture zones, but you do not have such a big area. For example, this one has been like 2,000 kilometers that's been subducted. But right now, if you see the evidence of that subduction is only being visible like 300 kilometers, and all of this the subduction has been gone. It's been like appeared in a slab. So in order to understand the configuration of this reconstruction, we need to see what is below India and Asia nowadays, and how does this subsurface look like. So here is so this is the work ongoing result that we are doing right now is a tomographic image. So for those who do not know much about the tomographic data, is what we use here is the P-wave seismological P-wave velocities, and we use it for the positive, and we classify them in the positive anomalies and the negative anomalies. Usually the positive anomalies belong to the lithosphere, and the negative anomalies belong to the mantle or the continent. So as you can see here, this is the line of section which is passing from very western margin of Pakistan, below Afghanistan even, and as you can see, this is the this is the subducting block, which we call as MK Makran block, and this is the impression of the Makran subduction zone. And here you have this Hillman block and Kabul block in the impressions, and then you can see the India. Now, this is the oblique subducting India. That's why you can see, or maybe Pamir and Hindu Kush zones, Pamir and Hindu Kush. So you can see this oblique impression. And this is the situation at first 1,000 kilometers. And as you move deep, you have this Arabia or Carlsberg anomaly. That is when the India was moving through the Arabian Ocean. So you get this Arabian anomaly. And then this is some old anomaly of the subduction known as the Mesopotamia, and this is Central China block. So these are the very western slabs that are visible in the tomographic images. The next one is the line of section that passes from Pakistan, and here you can see I could not select the better image than that. This is the line section which is passing almost from the center of Pakistan, and as you can see, the many things. This is the Indian continent. This anomaly is known as the Himalayan anomaly, and in the north you have the Tibetan anomalies. But if you carefully notice this anomaly, which is Arabia or Carlsberg anomaly, that is the oblique subducting India and Arabia anomaly, and known as Carlsberg slab. And then we have the India, that is the older impression when this greater Indian lithosphere, which I just said, it's been lost, like 2,000 kilometers, and you can see the volume of India is corresponding to that. And 25 million years ago, when Himalayas actually start to rise at its full glory, we have the slab break off in between India and Himalaya. So that's a different episode that slabs actually break off. And we have the presence of a new slab known as Himalayan slab. And then you have the nowadays, the present day image of the Indian continent. So that's how we can see these tomographic images, and these deeper anomalies that are present here is the Maldives anomaly and the Nepalese anomaly. These are the older anomalies, perhaps representing the Paleotethys Ocean. But let's try to compare this with the tomographic images of India. How does the India will appear? Here, this is the central part of India. The line of section passes from almost center, and here you have the Maldives anomaly and the Nepalese anomaly. This is the older Paleotethys Ocean anomalies. And then we have the subduction of India. So this is the amount of lithosphere that has been lost during the India-Asia convergence. And then the development of the Himalayan anomaly, and this DT is known as detached Tibet. So some part of the Tibet has also been lost. It's been subducted underneath India. And then we have the coming of Tarim and Kazakh block. And this is the Central China anomaly. So the thing to note here, the size of the Himalaya actually here is well grown. And if you compare with the previous slide, the Himalayan anomaly is shallow. But as you move towards the central part of India, it becomes deeper. So which means that the something at the western margin is not completely a vertical subduction. It's been oblique, and the slab is not sinking completely vertical. So it's oblique subduction. This is the line of section that I choose to show you. That's the east-west line of section, which actually, in principle, it doesn't make any sense. But if you know these north-south cross sections, then it will make a lot of sense. So here we have the line of section passing from the North Pakistan, and these are the Himalayas and the Burma. As you can see, the existence of the Indian anomaly, and this is the typical Himalayan slab. That is the volume of Himalayas that has been subducted below India. And this is the presence of the Indian continent. But as you can see that on the both edges, this India is subducting oblique. So this is the Hindu Kush slab, or we say that the Pamir. But Pamir and Hindu Kush, this Kufnar presented last year that these are the two different slabs, and at a shallow depth you can really differentiate. At a deeper level you cannot. On the other side, you have again the oblique subduction on the eastern margin. This is the Burmese slab, which has the impression quite similar with the western margin of India. So these anomalies represents the subsurface below India, and the amount of lithosphere that has been lost has been calculated, and we constrain the amount of shortening, and we restore back the oceans that has been lost. But how does it's really the point is what I try to show you here is the northwestern margin of India is quite significantly different as compared to the central part of India, as it has the influence of the oblique subduction at the western margin. And this western margin has actually created quite a different trend in the trend of the Himalayas. As you can see, the Indian side, the trend significantly changes when you move to the northwestern side, and here you see clearly that the trend changed and the western margin becomes very different. So you have, starting from the main Karakoram thrust, or known as the Shoyok suture zone, and just the north of that you have the Karakoram. And then we have Kohistan and Ladakh. Mostly all of the Kohistan is situated in Pakistan, and some part of Ladakh, like 30-40%, is still located in Pakistan. And then we have the Indus suture zone, and after the Indus suture zone, you have the development of main mantle thrust, which we consider that the main thrust responsible for the Indian subduction. And then we have the Greater Himalayas, or known as Higher Himalayas, and then we have the Lesser Himalayas, MBT, and all this stuff. And then we have the development of the Potwar Plateau and Suleiman Fold Belt. So this regional picture, as you might have seen already, what I try to show you here, this is not quite that you can see in India. The thrust belts or in India is actually, they are not very much, they're not well developed. But here in the northwestern margin, you see that these thrust belts have been prolonged, and they have transported a bit, like especially in the case of Potwar. Translation is quite significant, as you have the existence of décollement at the level of the salt. So we have the Indus suture zone, the main central thrust, and Hazara Basin, and then MBT and the Potwar Plateau. This is the generalized cross section. So here is the Potwar Plateau, and this is again a very generalized cross section. Don't take it as we will move to the very specific line of sections of the eastern and the western Potwar as well. But here, as you can see, that the this is the North Potwar deformed zone, and the after that you have the Swan syncline, which has the thick deposits of the Swan and the Siwaliks, and then in the salt range, which exposes the salt and everything. And the existence of this normal fault, which is argued by Lilly and other people. So this is the generalized line of section. So let's talk about the stratigraphy. We all familiar with the stratigraphy of the salt range, but for those who are not really familiar with, let me give it some overview. So we have the Precambrian or Eocambrian units that has been exposed in Pakistan as a salt range formation. And these formations are basically shale and evaporite series. And this thing, we actually don't know the original thickness of these salt range formation, but because of the salt has been active and it's been multiplied many times, so we don't know. But we actually do have the existence of décollement at the salt range level, so that so the tectonics is detached over the salt range formation. Then we have the Jhelum group, which represents the Kyora, Kasuk, Jutana, and Bagamala formations. And the Ordovician and Carboniferous is actually missing from the salt range, but we do have it in Peshawar Basin. And then in the Permian, we have the Nilawan and Zaluj group representing the glacial deposits and the shallow marine clastics, and the deeper marine Amberville Chidru formations. And then we have the Triassic representing Miawali, Tridian, and Kingriali, which is mostly exposed in the western Potwar. Also Jurassic, Datashnari Spanasuk mostly belongs to the western Potwar. Chichali, Lumshiwal, and Kawagar, Kawagar has actually been very less exposed, not very well developed throughout Potwar, but Chichali formation is well developed. Paleocene, we have Hangu, Lokat, Potala, and these are the clastics and limestones combined, and the Eocene represents mostly the shales and limestones, and that is what we say is the last marine episode in the Potwar and salt range. And after that, we have a transition starting from Murray and Kamlial. So that is the transition from marine to the continental zone. And after the Kamlial formation, we have a complete transition from to the continental shales, which is Chinji Formation, Nagri, Dogpatan, and so on. And this section actually represents the rest of the part of my presentation now, as it represents the part of the sampling that I did during my PhD. So the tectonics or the fault kinematics. So what we're trying to deal with here is the stresses that are responsible for the development of the Potwar. So what we did back in 2015 and 16, we collected more than 3,000 fault planes, and we measured them in the field. So one of the example is like that. So this is the Kalabagh fault, the strike slip fault, and we restored them back to develop the paleostress solutions. And we come up with certain solutions, and we have the dominant orientation of the sigma 1, 2, 3. And by this way, we can restore back the paleostress configurations in the basin, in the Potwar and salt range. Some other examples. This is from the salt range thrust, and this is actually the eastern margin of Potwar, which is a Jhelum fault, and this is the tensor solution that we developed. That we come back to that later. And so we have these solutions developed. Each of these solutions developed based upon the several number of fault plane readings, and then we combine them based upon the sites, and we come up with one dominant orientation of the major principal stress. So some part of the Potwar Basin is actually been brutally deformed, and the parts which are, especially with like Siwaliks, which are very poor in the development of the brittle or the rupture, These are very critical because when this deformation is actually passing through the Potwar, you have the deposition of the Siwaliks and the upper Siwaliks, and these sediments actually have recorded the events of this deformation. So what we use here is the array technique known as the anisotropy of magnetic susceptibility that can detect the strain in the magnetic minerals. So, for instance, you have magnetic minerals which are responsible for the magnetization of the rocks, like hematite and magnetite. And in a sample, we can detect that what is the major strain orientation in that sample. So for those parts, especially the central part of the Potwar, where the fault planes are actually hidden or filled with this Siwaliks, we sampled the Siwaliks for the AMS, and then we use AMS in order to interpret, to find the relationship of the stresses. So as you can see here, there is a major axis which is always almost vertical in most of the solutions, and we interpret that is the dominating compaction direction, as the sediments have the compaction more than stress. So we say that it's just the compression because of the compaction. And then we have another axis which is blue, representing you as the K minimum, what we say in the susceptibility tensor solutions. Here the K min is basically belongs to the folding axis. So we say that this is the strain in the sediments, and the remaining axis we interpret, which is mostly north-south, we interpret that this should be the stress orientation in Potwar. So we combine all of these samples and several sites, and we use them to develop the one stress map of the Potwar and salt range. And we also classified those in a different age group so that we can say that how does this stress evolves throughout the time. So here is so we divided them into multiple phase deformation. So we say that it's a two-phase deformation in Potwar. The first phase started at the pre-late Pliocene, and here you see that based upon the fault and AMS data, you have the development of this stress field within the Potwar. And this is the phase one. The second phase is a recent one, and starting from the late Pliocene. And as you have noticed that there is a significant difference of the trend, and these stress vectors, they fan out towards the Kalabagh fault. So which represents that this fault was well developed at that time, and you have this the activity of this Kalabagh fault majorly influencing the tectonics in the Potwar and salt range. Same data with the AMS. Based upon this AMS data, we classify that the existence of two different domains within Potwar and salt range. For instance, this eastern Potwar, which is almost north-northwest, and the other domain is your western domain, which is quite significant. So these arrows represents the major orientation of these domains. And this is mostly combined with the paleostress as well as the AMS, and with the both stage 1 and stage 2. As you can see that how the stress is evolving throughout Potwar and salt range. And these rose diagrams represents the phase 1 and phase 2 throughout the data. As you can see that the recent phase is very much similar with this AMS results, so they are not quite different from each other. However, the phase 1 was a bit different. But these are not the combined results. These are just the representation of each tensor solution, and we plot them in the rose diagrams. And this is the the combined results of two different phases. Here we have the first phase, which represents the almost northwest solution, and later it got evolved to almost north-south. So we have a change, a transformation of the stress throughout the Potwar in different times. Now, how does this stress affects the vertical axis rotations? So for those who are not familiar with the idea of vertical axis rotation, is you have the horizontal axis rotation, which we know as tilting, and the vertical axis rotation, which is along the one vertical axis. That means that you have the rotation along the vertical axis in Potwar. So what we expect here in Potwar is, if there is no rotation at all, and you have these lines which are continued throughout the Potwar, so you have displacement along Jhelum and Calabar fault, and no rotation at all. So it could be the one scenario, or it could be something like that when you have a gradual transformation from these Jhelum and Calabar evolving into the wider portion of the salt range and Potwar, and then going back to the very narrow thrust and fold belt, which is developed almost at the same time. So we should expect the geometries like that, and how these geometries affect the vertical axis rotation. So we combined most of the published data by Johnson's, Burbank, Opdyke, Tux, everything that has been published mostly. And these vectors, and we actually combined with samples that we made in 2017-18, like 2,000 samples more, which we think that is required there. And we plot everything together in the Potwar, and ignore the subdomains here. These are just the interpretations, but these vectors represent the vertical axis rotations. And we think that based upon these vertical axis rotations, we argue the existence of these domains. This could be the case because these, for example, you can find the anomalies within the Potwar. You would expect the counterclockwise rotation throughout Potwar, but you see that one of the domain here is completely representing the clockwise rotation, which we think that is influenced by these a set of strike slip faults that exist in the front of the salt range. But generally, rest is not really different, which has been already published. Just we try to divide them into the different several domains. Yeah, so here you have the idea that the major axis of rotation is vertical axis rotation is actually the counterclockwise. As you see, we have two sides also from the Kashmir block, which is the clockwise rotating. But here you have the anomalies, especially this one block, Mayal block, which represents the clockwise rotation. But overall rotation of the Potwar is counterclockwise. And we also try to see that how these rotations actually evolve through time. So what we have divided all the samples from is from the pre-Swan and Swan formation. So it means the Dhok-Patan formation. It's not only the Dhok-Patan formation, starting from Kamleal formation, going all the way to Chinji Nagri and Dhok-Patan until. And as you can see that it has the average amount of rotation is 21.3 degrees, and plus the alpha 95 of 2 degrees, with this, which we normally known as the uncertainty angle. But as you move towards the recent Pleistocene Swan formation, you have a very less amount of rotation in Swan. So you have almost 7.5 degrees with alpha 95 of 2.8 degrees. So which means that the vertical axis rotation is already been started when these Siwaliks were actually depositing there. And then by the time Swan formation deposited, the vertical axis rotation mostly happened, and very little amount of rotation has been stored in Swan formation. Now we see the basin architecture of the Potwar Plateau. That how does the subsurface look like in Potwar? I think the Hamad Ghani will explain better about this structural geology. But the reason I'm putting these slides here is to show you that these seismic sections are combined to develop these 138 kilometers section, which has been already published quite a lot of time. And what we see here is the amount of shortening. So that is 30 kilometers of shortening in the Siwaliks, and 13 kilometers shortening, which is observed only in the upper Siwaliks. So that is the different amount of shortening that is present there. But we generally compared with this shortening within the Siwaliks. So this is the eastern line of section, and this is the western line of section. We compare the same things. You have relatively more translation in the western Potwar and salt range, and it has the more amount of shortening here. So what we argued here is if you have the rotations in vertical axis rotation in Potwar, and you have less shortening in the eastern side of the salt range and Potwar, and you have the more translation in the western side of the Potwar, so you get this 30%. This green area is the amount of additional shortening that has to be compensated within Potwar and salt range. So this is the kind of situation that exists, and that is exactly the same as we defined as a domain boundary from the AMS and from the paleostress tensor solutions. And now the question becomes that when this rotation happens, when is where is the line when this different kind of two sets of rotations or two sets of deformation episode happened. So for that, we did the magnetostratigraphy. We went to the Mujahid section, which is the type locality of the Swan village, Swan formation. And that is the village in the North Potwar. And here you can see that the red dots represents the amount of these sites samples which we collected for this Swan formation. And this green line represents the projected sections of these samples. What we did here is we compared the magnetostratigraphy, and we tried to come up with two different options against the sedimentation rate of the Swan formation. And we concluded that this Swan formation is the oldest that you can find in this Mujahid section is 3.7 million years, which we think is the start of the deformation phase 2, and which is quite significantly different than the previous deformation phase. And as we also tried to compare the option 1 for the sedimentation rate, but it doesn't fit. The sedimentation rate goes extraordinarily crazy, which is not really possible. These ones, the 40 and 75, that is more realistic to us. And comparing that, of course, they have the different amount of vertical axis rotation already. We see that there are two different significant deformation episodes happened within the Potwar and salt range. And how now the question becomes how this regional Indian and Asian collision affects the salt range and Potwar. What is actually the relationship? So the relationship is, what we use here is the development of the structures versus the age has been already developed by these authors. What we do here is just to plot them against time. And here you see that there is a quite significant change in the rate of shortening. So at the start, around 5.5 million years, the Potwar start to deform at 4.5 millimeters per year, and later it becomes very fast. It becomes to 6.5 or 6.4 millimeters per year. So we think that these are two different slopes of the line, and these two slopes presents two different episodes of deformation within Potwar. But this is as compared to the velocities of Indian plate. This amount of this cumulative shortening is actually nothing. What we observe here. So normally what we say is the rates at which the Indian plate moves is like 30 or 40 millimeters per year. And but if you plot the same structures, same age, the distance between, considering the null structure as 0, and calculating the distance all the way to the Pubbie anticlines, and if we plot everything together, the rate of deformation propagation in Potwar and salt range is 30 millimeters per year, which is almost the convergence rate of India, suggested by Juan et al. At 30 to 40, 35 millimeters per year. So where is this 30 millimeters per year goes in Potwar and salt range? Because Potwar and salt range maximum gets to 6.4 millimeters per year. And there is a quite significant amount of this convergence has been lost here. So what we think is the only 18% of the convergence of India is been reflected within the Potwar and salt range. The rest is been accommodated is as the glide or aseismic creep within the Potwar and salt range, or the falls that are present in the north. They are accommodating more brittle shortening, and the Potwar is only accommodating 18% of that. So the take-home messages for today's talk is the oblique subduction of India at northwestern margin developed the mountain front quite significantly different as compared with the rest of the Himalayas. And the Potwar and salt range experienced two distinct episodes of deformation. So the first stage comprises of rapid vertical axis rotations and the slow shortening rates, and the second rate comprises relatively slow rotations and the very fast shortening rates. And the transition from brittle to relatively ductile within Potwar developed left lateral shear between Jhelum and Kalabagh fault, and this one affects the Potwar quite significantly. The first thing, you have the counterclockwise vertical axis rotation within Potwar and salt range, and also observed by the switching of the sigma 1 from northwest to the north-south orientation. And lateral changes within Potwar and salt range also affects the different amount of shortening. So the take-home message for today's talk is Potwar and the salt range is not really deformed in a single episode of deformation. It has been deformed in multiple episodes of deformation, which affects the vertical axis rotations, the value stress orientation, and the amount of shortening quite differently. So it's been considered that it's a single or rather continuous episode of deformation throughout the Siwaliks. It's not the case actually. It's this part of the work represents that they are quite significantly different from each other, and they have the different characteristics, and they can be used at the different age markers for the further basin evolution. So thank you very much, ladies and gentlemen. This is all of my talk, and I'll be answering your questions if you have any.
Yeah, great. Thank you very much, Kayam. Very nice to hear this presentation. And I think that now, if people have some questions, they can either unmute and ask the question out loud, or possibly you could ask a question in a chat, depending a bit on the forum. I don't really see the chat very easily here, but
me neither.
Yeah,
somehow.
So let's just request people who have questions, if you could just ask them, and Abdul, if you could be kind enough.
Yeah.
People.
there are a few raised hands. If Gary can check.
Yes, there is a question from GSP, so they can ask their question. They already.
Thank you very much. If you may hear me, Mukhtar Ghani, is my voice clear?
Yes, you can.
Yeah, sure.
Fine. So please let me introduce me. I am Adnan Alamawan. I am serving at GSP Islamabad, and it was a very interesting talk about the tectonics and the Himalayas. My question is about the summary of the last 2 decades research in this area. We all know that the big names like few who are present and Roger Billam and others who have altogether resulted in a very, I would say that a seismic alert is coming from the last 2 decades. And this was confirmed by the GNSS data since I would say that at least 15 years. So we all know this that this interplate coupling and seismic alarm is coming from few of the recent publications. And of course, GSP University's Center of Excellence and Balochistan University all are together and working on this topic, although working separately. But so my question in this background, my question is that now as it is confirmed that all this data of the convergence, shortening, MHT, and the risk along the MHT, where the seismic, as I said, I mean the interplate coupling, locking is very much obvious as compared to the previous studies. So what is your assessment of this whole scenario that this locking is going to be a risk as we don't have any reference big historical earthquake, we all know it. So what are your remarks about this seismic risk in the area along MHT in this area? Thank you very much.
So you talk about the Potwar and salt range. You ask about the Potwar and salt range specifically.
Yes, of course. This is right. All the geometries from the frontal thrust, and you have informed us that 80% shortening is along this MFT and the salt range Potwar, and then the rest of is somewhere in the upper Himalayas, other parts. So yes, I mean 18%. So
Yeah,
right.
Yeah, I get the question. So yeah, thank you very much for that. Well, if you ask in my my technical opinion, I would say that Potwar and salt range, they are rather the safest area in all of the northwestern Himalayas. The reason why I say that is actually your decolme or the decoupling over the plate is at the horizon, which is rich in salt or the evaporites. So all of the deformation that has been happening, or all of the translation or the detachment, that's within the salt. So salt actually deforms itself, but the rocks that are above salt, they are not really deformed brittly. So as you can see that you can imagine the salt behaves in subsurface like a liquid, so it flows. And it carries all the sediments over it without any brittle deformation, or without very minute within deformation. So, for instance, if I can share something, the earthquakes.
Yeah.
For example, the earthquake records there in the Potwar and salt range. Let me share my screen again. A moment, please. So this slide here represents the earthquake records plotted in the northwestern Himalayas on the tectonic maps. As you can see that we have very almost no major events throughout the Potwar and Kohat. It's almost nothing. So you have major events coming from the Hazara-Kashmir syntaxis, the main mantle thrust, and especially as you can see here. So this is where you have Pamir and the Hindu Kush subduction zones, and these are very deep earthquakes, and going to the unrealistic depths like 300 to 400 kilometers. So in my opinion, in my personal opinion, I think the Potwar and the salt range might be the safest area within the region. But as you move towards north, yeah, there are quite significant risks, especially along the Hazara Kashmir syntaxis, the Nanga Parbat syntaxis, as you can see, as it's been evident by the data.
Yeah. Yes, I would exactly agree with your remarks, because in recent GSP French publication, you must have seen that. And in this, the same opinion is about the salt range and Potwar, and same opinion as you said about the upper area. So now the question is that what do you think that we have a collaborative researcher strategy in Pakistan, that we sit together, all the researchers, and define the objectives, targets, way forward in this upper area, because you know the MHT, the other players in the upper area, and there is locking. And this is, I think, an information that GSP has now communicated to the disaster management authorities. We have also included KP, disaster management authorities, and other. So all are on board. But we have recently initiated. GSP has organized a one-day workshop. I mean, just it is the background. So how you look forward on this locking the décollement along MHT and this seismic rig? How should we collaboratively move forward? Thank you.
Yeah, well, I think you guys are already doing a great job there. I know you guys have installed the GPS with these French guys, and you have actively data coming from all over the Pakistan. Well, for the collaborative effort, what we need is the problem becomes big when it comes to the data sharing. So if you don't have the issues with the data sharing with not me, with the rest of the teams, yeah, we are on board. But if you have certain audience that you want to work with, or you want to address only certain number of universities, or your GPS, for instance, belongs to some university, then it becomes problematic with the collaboration. I guess this forum is all about the collaboration. That's why Bob gathered all of the people here, and that's why I'm here. That's why you're asking this question. So that is not an issue that we are not on board. We are on board. We need to rather address the issues of this data sharing and the realistic problems. You know, these if we can openly come up to a platform and discuss that we have this problem and we have this data and we need to have this approach with that, and I think that will that everybody will move in a constructive way forward.
Yes, I mean, thank you very much. Just concluding my last sentence, that GSP has now actually forward a proposal to all the stakeholders. We all know UNEVCO, that it is a worldwide platform where GNS and GPS data is shared. So on the similar pattern, GSP is organizing a get-together in the March at Islamabad, where we will invite all the national stakeholders. And this is one of the agenda. We have a few other agendas. So making use of this platform, I thought to inform you and our other researchers.
Yeah, thank you very much. Thank you.
Doug Burbank has a question.
Yeah.
Oh, I was wondering if you could put back up your slide 32 from your presentation.
Yeah, sure. Yes.
I was curious about why you correlated your N3 magnetic zone just with the top part of the Gauss. And from my reading of this, it looks like you would have 2 millimeter per year accumulation rates during that interval, which was sort of faster than we ever see, or that I remember seeing in the mag strats around there. And why don't you correlate it with the entire Gauss? And just, I don't know how densely that magnetozone has been sampled. It's certainly true that N2 and N1 don't provide convincing, to me, matches to the rest of the Gauss. So I've just wonder both about the timing, the duration, and then, of course, the rates of rotation that implies.
Yeah, well, what we have here is what we think is it's the top part of the N3. The reason that you can see here is that we only show these the Swan Formation, and then we moved to the softer part of it. We actually went to the end of the Matuyama, and that's why we actually separated this from this Gauss. And yeah, I mean, there is the rates here is actually we sample 870 meters of section, and we have only, I think, close to the 40 sites.
Less than 500,000 years.
Yeah. So yeah, I mean, even within Swan Formation, it's been very difficult because it's mostly very coarse sandstone. You need to you need for PMAG or MaxRad, you need to have the soft horizons, and sometimes the sedimentation rate is so big that you just find coarse sand and you cannot even sample there. So it's been it's the best I think we can do, and yeah, if it's not working, then yeah, I mean, I know you're more expert in that with that, but this is what we have right now.
Well, it's always a trick when you're trying to just match,
Yeah,
pattern,
but
it's a challenge.
Yeah, but the trick here is I think the base part of the Swan, which we think that is the point where the second phase of deformation started, and it continues that we don't have this high resolution to continue until recently, and then we can say that, oh, there is one more deformation episode existing in this area. So this so we just place the boundary here at the base of the Swan Formation, and we think that's the point where you have the second phase of deformation, because clearly even in the field relationship you can see that if you ever been to this Mujahid section, the relationship of Swan and Dhok-Patan Formation is actually 90 degrees. So you have the Swan Formation that is almost subhorizontal, and the northern edge of the Swan syncline, you have the Dhok-Patan Formation, which is almost vertical. So when you have this kind of relationship, you already know that this deformation is clearly it's not been involved in the same episode of deformation. It's been different, or Swan Formation is actually postdates this deformation event.
Okay.
So we have a question from Catherine Beasley. Please unmute
yes,
yourself.
thank you. Sure, thank you for an interesting presentation. I'm curious to know whether your tectonic reconstructions have implications for the establishment of the Indus drainage.
Well, okay. For Indus drainage, what we think, you mean specifically for the Indus River?
Evolution?
Yes.
Okay.
Yes.
So, yeah, what we think here for the Indus River, I mean, that is the thing that we just discussed in my discussion part of my PhD. So we think that it used to flow from the Potwar, and it actually comes within Potwar, somewhere close to the where actually the present location of the Namal Lake is, and then this development of the Miyawali embankment happened, and the Indus River actually shifted from Potwar to the west. And you have these Swan River majorly dominating there. So it used to flow down there towards the Namal, where the present Namal Lake is, and then it flows out of the Potwar there. And nowadays, presently, it's successively moving north, And if it's continuing like that, it will still further step up in the north and pass probably somewhere in the north, somewhere close to the Kohat.
Thank you. I'm curious partly because in the middle Siwaliks, where the Harvard GSP group has worked, we find the current directions are mostly to the east and flowing along the mountain front, as if they are part of the Ganges system. So I was just wondering when the Indus comes to enter the area.
Yeah, that is possible, but we also think the possibility of the influence of the Jhelum River. So before the influence of the development of the Jhelum Fault, what we think here is it used to flow in the present-day location of the Swan River. And as you develop the Jhelum Fault, the Jhelum River turns around along this Jhelum Fault, and only the Swan River flows through actually Potwar Basin. And Jhelum follows the Jhelum Fault and goes down to the Salt Range. And Swan continues partly with this Indus River system. And then, so it could be both. You have the Jhelum River flowing all the way from Potwar, joining the Indus River system at Namal, and then all together they flow there.
Thank you.
Okay, thank you. Now we have another question from Lee Ong. Now you can unmute your mic, Lee Ong.
Many thanks for the wonderful presentation. I want to take your general opinion about some of the, as we are going to construct some massive structures along Jhelum River. And, this is something very risky in active area like the Jhelum running along the Jhelum River, and we have MBT also there. Do you think this is safer construction? And the other one we have already constructed is Neelam Jhelum hydropower project and Patreen project. We have already constructed two massive giant structures. And in Rawalpindi, we are observing that there is subsidence is going on in Rawalpindi area. So do you think we have already constructed a metro line which is about 22 kilometers, and it is most of the part is overhanged? Do you think these structures are safer for our future prospects in our future? If we think there could be a disaster along or an earthquake along Jhelum Fault or MBT, do you think these are safer or not? I want to take a general opinion about this. Thank you.
Yeah, well, as far as the bigger structures like Neelam Jhelum is concerned, that is actually a bit of a risk because it falls close to the vicinity of the Hazara Kashmir syntaxis. And as you can see, evident from the earthquake data, you have the accumulation of most of the earthquake density there in the Hazara Kashmir syntaxis. So that is I don't know what kind of safety parameters that you use there, but that is actually a risk. For the smaller structures like metro stations or overhead bridges, yeah, even if you have some subsidence going on in there, what you will get maximum, you will have the collapse of some pillars, and then you would repair it. That is all. Still, you have 27 kilometers. I don't see any possibilities that in a single event that this big structure of 27 kilometers will collapse at sudden. Yeah, of course, it's close to the MBT, and we already have experienced major earthquakes along the MBT. I mean, local damages are always an option there, but I don't think the bigger structures is a risk. And it mostly depends upon what thresholds that you used. You actually made these structures earthquake proof for this area. I assume that all the buildings that it's been done, like the Neelam Jhelum and the metros, there is actually at least 6 Richter scale proof structures. If not, then yeah, I mean, there's no guarantee. I cannot say anything that, you know, the structure will remain or after an earthquake or not. So it mostly depends upon the safety parameters that has been used there. And always, you know, there is a risk to the earthquake. This is the active zone, plate tectonics zone. So yeah, you cannot avoid earthquakes there.
Okay.
But my question is, this as a geoscientist in Pakistan, we don't have a platform to address these issues, and I am following the news that nobody is talking about this because I am working on some geohazards along the Jhelum River. So I have seen 6 mega structures we are going to construct in 10 to 15 years. So do you think these mega structures can activate the Jhelum fault or MBT? It's very simple, I think.
Yeah, well, I mean, these mega structures will not activate the Jhelum fault and MBT. Jhelum fault and MBT is already active. And these structures can be activated by the activity of the Jhelum fault and the MBT. So yeah, if you ask my opinion, I think the Jhelum fault is relatively consuming the brittle deformation as compared to the Calabar fault. So more you stay close to the vicinity of the Jhelum fault and Hazara Kashmir syntaxes, it's not really safe. You rather wants to make something below, close to the salt range, where you have where the salt range meets the Jhelum fault. That would be relatively safer option, I guess. But not in the north, close to the Hazara Kashmir syntaxes and MBT. No, it's not.
Okay, so now we have a question from Andrew. Please unmute your mic.
Hello, thank you very much for that very interesting presentation. Could you explain again to me how you figured out the rates of shortening and especially the variation in the rate of shortening towards the end of your talk? I didn't completely follow that, I'm sorry to say.
Okay, yeah, I'll get back to the presentation for you.
Thank you.
So, you're talking about this rate of cumulative shortening, right?
Well, you had some plots that showed shortening in time, and you had accelerations. Yes, I did. This is the part I wasn't quite following.
Yeah. Yeah. So here, what we did is to use these references. So these guys have dated the individual structures. Okay. So these individual structures has been plotted against. So we have this table, which represents the amount of shortening at the structure, a total amount of shortening that has been consumed. I did not make these tables. These guys have individually dated these structures and come up with some age. Yeah, there are some ages which belongs to us. And what we did is to plot here the time versus distance, and you get these rates, different rates here. And as we can see that, you know, these two lines have two different slope values, and we are convinced that it has something to do with the two different episodes of deformation that we see in the paleostress configuration, in the rotations, and in the shortening amounts. So that's how we come up with that. We actually come up with one more thing that is called the rate of deformation propagation or the rate of convergence. So this is the same table, and what we use here is how the one structure is being activated from another structure, and how the deformation propagated throughout the Potwar region. And then this is actually the same rate that you would expect for Indian plate. That is what the GPS velocities would show you. But the amount of shortening that that is something different. The amount of shortening is actually how much a structure is representing that the amount of shortened crust is there. So these are two different things, and we compared them, and we say that okay, there is a loss of this shortening and the displacement propagation, and that much amount of the Indian plate has been consumed within Potwar and salt range.
So for any pair of dot points on that plot you just showed,
yeah,
what you were doing was summing up. Like, for example, you have a dot at 4 million years and you have a dot at 2.5 million years.
Yes.
The shortening between those two dots is the sum of the values in that table for that time interval. Is that correct?
Sorry, say again, please. The shortening?
Well, I'm just wondering what each one of those dots represents. Is that the sum of the amount of shortening for any sets of structures in the table over that time interval?
Exactly. Yes, so you have the total amount of shortening here and versus the time of deformation initiation. So you have the time versus the total amount of shortening within the Potwar and salt range, and against each structure, and then we plot this total amount versus the time, and you come up with the curves.
Okay.
Yeah.
Thank you.
Okay. So we have another question from Hamad Ghani. Hamad Ghani, you can unmute yourself.
Thank you, Qayyum, for a very nice talk. And indeed, this is one of the continuation of new results into this area. So my question is that when we look at all the previous paleomagnetic studies, we see that all these studies have somehow shown that the eastern part of Potwar has some rotation. Like this part, eastern part has experienced this counterclockwise rotation. What new came up in your research is that you have shown some clockwise rotation in the western part, which is in these previous studies were not actually mentioned in that. So what, how you come up to this conclusion? Did you went to new areas, or it is somehow the development in the method which lead to this conclusion? Thank you.
Yeah, thank you, Hamad, for this question. I think this is one of the most important questions there in this area. Most of the previous work suggests the counterclockwise rotation, and the clockwise rotation that we observe here is not the new method. It's actually the same method, but the resolution of this data might be, or the resolution of or accuracy of the machine that is measuring the remnant magnetization would be, I think, more advanced. Because these samples were taken recently, and the data represents a high resolution sampling. What could be the factor here is what we think. If you're asking for the reasoning why the clockwise rotation in this particular one block that we observe is let's see. So you talk about this Meal block that we have here. That actually what we see is the clockwise rotations, a few degrees, not much. So it's here, it's like 10 degrees or so. And these rotations are argued for the presence of this conjugate set at the salt range thrust. So this conjugate thrust set is known as the Pal-Washnal strike-slip fault and Caneti strike-slip fault. And movements along this strike-slip fault, as you can see, it's very much it's the strike of the salt range. You see the clear difference here, and we think that the displacements, some extraordinary displacement along this strike-slip set could offset this block slightly more than the rest of the blocks within Potwar and salt range.
So we have another question from Gary Johnson. Please unmute.
Yes, thank you for a great talk. You made a comment about the Ceylon Formation overlying Dok Patan at about 90 degrees. If you recall, just south of Rawalpindi, probably on the order of 3 kilometers, down in the Ceylon Valley, the volcanic ashes that we've dated that straddle roughly the Gauss-Matayama boundary are in vertical position, and there is probably another 40 meters or so of sediment that is also vertically aligned just above that. So that takes us perhaps to maybe 2.4 million years ago or so. And then on the north bank of the Siwalik, or of the Ceylon, there's nominally flat-lying rocks that are demonstrating the Olduvai event as well as a datable volcanic ash. So you do have pretty good evidence there that at least through about perhaps 2.4, 2.3 million, you were in this one tectonic scenario, soon to follow by that major disruption and end of phase 1 before you go into phase 2, which is dominated by the Ceylon Formation of phase 2 deformation. So the best place to see it, I think, is, well, actually one down by Domeli, but also that Ceylon Formation area just south of Rawalpindi, where you can actually see these two things in juxtaposition. Thank you.
Yeah, that is something that we also noticed, but I think at the time I was not planning for the radiometric dating because the other workers are doing that, and I had the option in the project for this magnetostratigraphic dating, so I opt for this joint section, which is the northern limb of the Swan syncline. But yeah, I do noted that, and I knew that you guys have data and which is already there. So I just used that thing as a reference for the further development of this theory.
We were looking at Google Earth the other day and realized that the evidence for the lower sequence has been completely buried by new development of some suburbs of greater Rawalpindi. So it's been cremated by a bulldozer.
Yeah. But I do have a site there for this Swan rotation somewhere in the Swan Valley. But that's for just to see the amount of rotations there.
Very good. Thanks.
Thank you very much.
I think we don't have any other question.
Let me just break in a little bit here. I feel like this is a wonderful presentation, Abdul, and you've covered a lot of ground, and I think that it's an opportunity to illustrate the chances to bring together research done over different time periods and to sort of to answer Doug's question and to feed into some of Gary's comments. It would be interesting to take the work that you did in the Mujand section and see how it maps around to the other paleomagnetic sections that have been done, for example, in the area around the Rawat Fault and Kasdovak. There's a lot of data there, and it could be interesting to look at it in map view. And some of that is available on that website. If you look at the Siwalik Stratigraphy website, you'll see some of that data that has been charted, and it'd just be interesting to put together. The other thing, just to comment on the seismic risks, I was particularly interested to hear some comments about the GPS data sets and the UNAVCO collaboration that the GSP is involved in. And I think that there's no question that the Potwar region and the MCT and the MBT, et cetera, are actively moving and are certainly capable of rapid deformation and creating earthquakes. I think it's wonderful to hear your comments, Abdul, about the safety of when you're sitting on top of salt, you're in a relatively safe place. But then, as you look at the bigger infrastructure, including some of the big dams that have been built in the past and future projects. Those are in more perilous areas, perhaps. And I think that as an earth science community, we do have the opportunity to use the historical data that you've been compiling together with the modern data associated with GPS measurements of deformation active, and to help people better understand seismic hazards. And I think that's a very fascinating topic, and one that we as a community could follow up on. So I'm delighted that that's come up as a topic of conversation here tonight.
Yeah, we have another question probably from GSP.
Thank you very much, Bob Renaud. That reminds your visit of Quetta, and where we were together, I think, a few years back. So just to update the researchers that Pakistan Engineering Council is now on its way to revise the building code of Pakistan. And this is in fact an activity after 2007. We all know that our published data is Building Code of Pakistan, Seismic Provisions 2007. It is now being updated. So my question to the researchers or the fault custodians who have worked on different faults, because this system is not interlinked. Whoever supplies or communicates the fault data to the people who are working on this building code, maybe they are not connected. So this is just a suggestion that this is one of the important documents, because the people there informed that 93% of the buildings in Pakistan are not according to the building codes. So this is just a comment from there. So this is an avenue which needs to be focused in the future. Thank you.
Well, very good. I think this is an opportunity to sort of draw to a close. I think it's we've had a wonderful, broad-ranging conversation. It's covered geotectonics. It's covered methods of measuring, rates of change through time, and these are topics that we'll continue to discuss. I think Catherine Badgley's comment about the evolution of the Indus River, the course of flow of the Indus River, will come up in further discussions. And I think that the point that I always have thought about as I look at the Google Earth maps or the Landsat imagery maps of the Potwar Plateau and the Peshawar Basin is that we see the world today, and we almost think it's always been that way. We think the Indus River's been there, the Jhelum River's been there for a long time, but the geological record tells us differently. And these landscapes have evolved really dramatically in just the last few millions of years. So in post-Miocene times, the geomorphology of the Potwar Plateau, the geomorphology of the Kashmir Basin and the Peshawar Basin have changed dramatically. And the rates at which these changes have happened are astonishing, and perhaps not too surprising when we look at the plate tectonic setting that Abdul has shown us. But I think it is a reminder that the geoscience community has an opportunity and maybe an obligation to convey these concepts. Example would be the seismic hazard map. You know, the seismic hazard map should be always updated, and the building code story should go hand in hand with the understanding of the seismic hazards. So I'd like to thank everybody for participating this morning in Pakistan, this evening in the United States, this early morning, Abdul, in Utrecht. And we look forward to seeing everybody in 1 week's time. And Catherine Badgley will be giving us a presentation on the interpretations of some of the data derived from the Yale Harvard University GSP collaboration that John Barry spoke about at our previous meeting. So thank you all very, very much for your participation. These talks are recorded, and we look forward to seeing you again next week.
Thank you. Thank you.
Thank you very much.
Thank you. Thank you, everyone.
Thank you all.
Abdul, good morning, and thank you again.
It's been an honor presenting to you guys. Well, I hope everybody must have learned something. Thank you very much, everybody.
You know, it's very wonderful, and the graphics are very beautiful. And I love the one that's on the screen right now. And I think that it's an opportunity for really for yourself and your team, Abdul, to carry that further and let people better understand the compartmentalization of deformation, the fact that there are these segments both in time and in space. And I think that that's something that would be of great interest to follow up and future research in the area of the Potwar Plateau and going up into the mountains would benefit from this kind of analysis.
Yeah, sure. Since I started my postdoc, I'm always been planning to come up here for the fieldwork, but unfortunately couldn't. So we have to focus on the other parts of the project, which is the subsurface, remotely doing the geology. But yeah, as soon as we can, we will. We already have some plans of going back to Pakistan. I already have some. My drill there, which is with me, and if anybody, not only me, if anybody else wants to use it, you can borrow it from me and get the sampling done and use it for whatever you want.
That's very generous. That's good, and I think it's important to appreciate that there's a young group of students coming forward at Punjab University, your own school, and also in Peshawar University in Quaid-e-Azam, and also in Balochistan. And I think that the young students are looking for projects. They're looking for research that is applicable to public safety and to the needs of the Pakistani people. And I think that your advice in that dimension could be very valuable and very important.
Yeah, sure. I'm always looking for some help. Always looking for some collaboration, and if we get the mutual benefits, why not? Yeah, that's what's it all about.
Yeah. Great. All right. Well, thank you all again, and thank you, Mukhtar, again for coordinating and being our host in Quetta. We really appreciate it very much.
Yeah, thank you very much.
Thank you, Mukhtar, for arranging everything.
Thank you.
Okay.
Okay, bye.
Goodbye, everyone.
Yep. Yeah, Hoda Hafiz, good night.